means natural. What is natural? What do you mean by natural? Can anybody give me the the basic idea of organic? We are now learning about how to analyze the organic analytes using chromatography methods. So explain to me what this basically means in your words, your own words. What is organic? Living metals, like previously, who said that? Anis, okay, yes, quite correct, but it's not so accurate. So what is really means by organic? We are as a chemist or engineers, okay, the basic thing that we need to know about organic, what is it? The substance or the compounds that is made from what?
Uh, Compound containing carbon.
Yes, exactly. Okay, compound containing carbon. Okay, carbon and hydrogen. Good. Okay, that is the basic things about organic. Okay, we are now discussing about organic analyte. So organic means the compounds that contain carbon and hydrogen. Okay, you are as petroleum engineer. Okay, one day you will dig the mother earth for the sake of the oil. So what is oil? What is oil? You're gonna drill this mother earth to take that thing. You are petroleum engineers one day, right? So what is oil? Oil is something that is really organic, right? Am I true? A lot of what? We call it what? Hydrocarbons. So that is organic. Hydrogen and carbons. Okay. You dig this mother earth, okay, for the sake of the oil. Okay, and then the oil is hydrocarbon. So hydrogen and carbon. So that is organic. Okay. In the oil and gas industries, one day you will get into that industries. Hopefully, inshallah, right? So you will this chromatographic method is really important to analyze the hydrocarbons. Okay, understood? Okay, so
Yes, Doctor.
okay, now we know that the organic analytes is basically means the hydrocarbon compound. So the technique to measure or to analyze the hydrocarbons of the organic compound is chromatography. So what is chromatography? Chromatographic method. Okay, what is the basic principle? Right? Now, this is simple from chromatography. Okay? So you cut a piece of tissue. I want to I want to give a simple assignment for you guys for today. Okay, and then you will show me the proof just in the WhatsApp group. Okay, you cut a piece of tissue and then you put any solution that have colors. Okay, you have your mother's cooking and ingredients at the kitchen, right? You take the coloring agent, okay, Star Brand, whatsoever that you have for the cakes ingredients at your kitchen. Take it and then put a dot on the tissue at the at very end of the tissue. You put one dot of the any coloring thing. Is it no matter if is it natural, such as a fruit that has colors. What kind of fruit that have a really intense colors, such as dragon fruit, okay, or anything that you put at the very end of the you cut the tissue in the shape of rectangular, okay, and then you put the very end of the tissue a simple dot of the coloring solutions, and then you will see all those things. It's moving, right? It keep moving on the tissue. Am I true?
Yes.
Okay, you can see the first dot. Where is my pen? Sorry. Okay. You see the first dot was put here, and then it's moving up there. The first dot was red and then become lighter, and at the end it become yellow. Okay, and this one, it might be also red. I don't know which part, which direction the coloring solution go, this way or that way. Okay, but the color is changing, right? Am I true?
Yes.
Can anybody have tissues now with you? Can try. Okay. Now wait for a moment. I want to attach some gadget to my computer so that I can easily annotate anything on the screen. All right. So you basically now you don't have any idea about chromatography yet because I'm just showing you a tissue, cut of tissue, right? And a coloring solution. So what is its relation with the chromatographic method? Oh, now I have a pen with me, right? No, to tissue I have a lot of gadget. This is my, oh no, and invisible pen. Okay? It's quite spooky. Okay, right. So this is the chromatography, the basic of chromatography. You can see we put. Oh, what happened? I don't have any ink with my pen. Why? Do I need to click? Wait, I want to test my pen. What happened? Okay. Oh, the mouse is functioning, but not my invisible pen. It's okay. All right. So all right. So this one is a very simple, a very basic theory or concept about the chromatography, and this is the advanced chromatography system. Okay. So from these two figures, can anybody tell me? So what is the basic idea about chromatography methods? Do you have any idea? Nuril Irfan, you have any idea?
Separate,
Maybe
identify,
color.
analyze.
Okay, Irfan first. Okay. Irfan? Nuril Irfan? Or you give ladies first?
Color.
Huh? Color?
Color.
Color, okay, color. Okay, Anis, what is your idea?
Separate or identify, analyze.
Separate. Okay, I like the word separate. Okay, Irfan said color. Okay, and Anis said separate. Okay, if we have colors, so how do we separate? That is my question. We see we have colors here, and then it being separated. Blue separated with the yellow, the red separated with the pink and yellow, the green separated with the indigo. So how it being separated? I want more answers. Based on what? It being separated based on what? Okay, how does it being separated?
High, sir. Ketinggian dia.
Based on high. Okay. Explain more. How it being separated based on high?
Setiap color tu dia ada batas dia sendiri.
What? Ada apa?
Batas dia akan ada Mana?
Batas,
Limit,
okay.
limit,
You,
limit.
you got the idea. Every colors have the limit. Okay, what makes the every every colors in the compound have limit? What make it have a limit? You see that they have a limit, right? Now, what make it have a limit? For example, okay, I gathered all of you. How many all of you? 49, right? I gathered all of you in one room, okay, one closed room. I don't know. I didn't meet all of you face to face yet, okay, but I'm pretty sure that you have a lot of size. Okay, let's say in that room we have no doors. It's closed room, okay, and then I create a one door that is really small. That anybody that have a weight of 60 and above can pass through the door. So not so many of you can pass through the door. Only those who have a very tiny body, right? A slim shady, right? Okay. Only few of you can pass through the door. Okay. That is the limit. Okay. So someone that have a really big size like me, okay, cannot pass through the door. Meaning that I'm outside of the class. I'm outside of the room. Okay. Okay, so you guys in the closed room, and then I make a tiny door. Not all of you can pass through the door. Only those who have a weight 60 and below can pass through the door. So now what is the limit?
Size.
Size. Okay.
Molecule.
Molecule. No, we are talking about you. You can pass through the door with the molecule. Yes. Because of your size. And some say that because of your weight, right? So that is the limit. Okay? Understood? Every compounds in the sample, okay, have the limit. Not all the compounds in the sample have a similar weight, similar size. What else? Now don't think in the closed room anymore. Okay, you are now outside of the closed room. Now think about the compounds, the molecules. Now you are talking about the molecules. So every molecules have different solubility, right? Different solubility. And what else?
Polarity, ionic strength.
Yeah, so you have read the notes, right? Anis have read the notes. Okay. So under the separation method, we have chromatography method. Okay. So what this means by chroma? Chroma means color. Okay. Graphy means write. Okay, this is basic words of the chromatography from the Greek words. So it's a combination of chroma, color, and graphy, write. Okay. So it's described a variety of separation techniques based on the distribution or partitioning of analyte, the solute, between a mobile phase, okay, solvent, and stationary phase. Okay, in this chromatography methods, we will talking a lot of words, the similar words. For example, the keyword is mobile phase. Okay, the solvent. In chromatography method, we need to have a mobile phase, which is the solvent. Okay, and there are a lot of solvent, lot type of solvent that is different different analyte will use different solvent. Okay, and then we have also stationary phase, which is the column. After this, we will discuss. So this technique was founded in the 1906 by Michael Schwartz, a Russian botanist who separated plant extracts on a column packed with fine calcium carbonate. Okay, so The column packed with fine calcium carbonate is the what phase? Mobile phase or stationary phase? Does the column move? It's still there, right? It's stationed there, right? So it's stationary phase. The fine column, okay, packed with calcium carbonate is the stationary phase. Okay. So the sample, so basic principle, the sample molecules, analytes or solutes are physically separated by distributing themselves between two phases. Okay, stationary phase and mobile phase. Okay, so that is a packed column. Okay, for example, this is a calcium carbonate packed column. So it is the stationary phase, and we have our sample there. A lot of various shapes of sample we have one sample, and then in the sample we have a different shape of analyte. Okay, and then we put something to flow the sample. That is a mobile phase. Now understood? Which one is mobile phase and which one is the stationary phase? This one is the, oh, now my pen has the ink. Okay, this one is stationary phase, and then we put something, right? That one is the mobile phase, right? Does the stationary phase move?
No.
Okay. Does the mobile phase move?
Yes.
Yes. Right? This one moving, this one is being stationed. The word is station. Does your bus station move? No. Your bus is moving, right? The bus station is still there. So the stationary phase, okay, normally called as column. Oh, my bad handwriting. Okay. Normally called as column. Okay, now a stationary phase, a solid packed into a column. Okay, in the layman word we call just column. Okay, so it is solid packed into a column. Okay, a solid coating the surface of a flat plane material, also called a stationary phase. A liquid supported on a solid, also categorized as a stationary phase. Okay, a liquid supported on the inside wall of an open tube, also categorized as the stationary phase, because it does not moving, it's still there. The one move in the system is the mobile phase, which is the solvent. Okay, so the mobile phase is a gas or a liquid or a supercritical fluid. Okay, now why we do chromatography? The word is to separate, because our technique is separation method. Our method is separation method. The technique is chromatography, right? To separate two or more compounds in a mixture based on the difference in the property of each individual substance. Okay. So, what is the property of the individual substance which are different? Polarity. You have said before this, right? Solubility, ionic strength, and size. So this size is related with what? The molecular weight, right? Right. So this is the example. We have the mixture of compounds. Okay, two or more compounds. Remember, if we said mixture, we have two or more. Okay, if we have only one compound, that is not a mixture, right? Okay, so we can see here we have a large compounds in the yellow color, and then we have the medium size of compounds in the red color, and we have a very small compounds with the black color. And then we need to separate all of this. We need to identify what is this, what is this, and what is this. Okay, then we need to separate. Okay, so how to separate? We use the chromatography technique. Okay, So we at the end of the process, we successfully separate all the components. Okay, this is the large compound. This is a medium-sized compound. This is a small compound. It's different properties, size and colors, for example. So we now can analyze, we can identify, we can purify, and we can quantify. Okay, we can analyze what it is. Okay, based on the properties. Okay, and then after that we can identify. Oh, so this is, for example, this is the this is CH3, for example. Okay, so this is CO3, for example. This is just for example. Okay, and then this is what? Oh, this is just C. Okay, so now we can identify. So after that we can purify. Okay, we only want this thing. We eliminate this thing and this thing. So now we are purifying the compounds that we want. Okay, and then we can quantify. We can quantify the compound that we have already purified. So how many of the compound we have? 1, 2, 3, 4. So we have 4 CO3 molecules. That is for example. Okay, so this is how the chromatography works basically. Okay, most useful analytical method for separation, identification, and quantitation of chemical compounds today up to now. So this chromatography technique is the best one. Every industry in this world have chromatography instruments. The most famous one is what? Can anybody give me the example, the idea? What is the famous, very useful chromatography instruments in the industry? Oil and gas industry, food industry, pharmaceutical industry. You just said it. Any industry have these instruments. Can anybody give me example? I don't want to hear from Anis and Irfan anymore. I want to hear from somebody else. Let me pick your name. I want to hear from Patricia Uzma. Are you there?
Yes, sir.
Okay, so what is the famous instrument of chromatography technique in the industry?
In which industry? Any industry?
Any industry.
I think maybe the photosynthesis chromatography.
Photosynthesis chromatography.
Yes.
Okay. I will think of that. Can anybody else try? I will pick your name.
Separation of oil and gas. Betul?
Who said that? Hakim Pao.
Separation of oil and gas. Can.
What was your answer?
Separation of oil and gas.
Yeah?
Separation of oil and gas.
Yes. What is the instrument?
Using like chromatography can. Betul?
Chromatography is the technique. So under the chromatography technique, we have a lot of instruments. The machines. Okay, it's okay. So you don't get the idea that, now. So, for example, we have HPLC and GC. These two instruments are very famous, very well known, and very useful in any industry. Okay, oil and gas, foods, pharmaceutical. Just said it. Okay, a lot of industry use these instruments. So what is HPLC?
High performance liquid.
Yes, high performance liquid chromatography. Then what is GC?
Gas.
Gas chromatography. So what kind of analyte being analyzed using HPLC? What phase of analyte? The answer is in the name.
Liquid.
Liquid, right? Liquid. Oh, very nice handwriting. Okay, so what is GC? What kind of analyte phase? Yes,
Gas.
Silva. Yes, gas.
Yes.
Gas. Okay, so how we need for liquid is simple, right? So we bring the liquid sample and introduce to the instrument, and then we can analyze. So how to analyze a gas sample? Not sample. So how this instrument analyze gas? So basically, we also introduce a liquid sample, but the instrument itself will transform the liquid into gas, right? And also for this instrument, also we can use solid sample. Yes, solid sample. Solid sample that can be transformed into gas. So after being transformed into gas, then the instrument will analyze the analyte. Okay, so similar with the spectroscopy method, we have two parts of the two components of the instrument. Okay, sorry, need to move it. So we have two parts. Okay, the first part is for the I want you to answer this. Okay, the second part is for the detection. And for the first part, previously in spectroscopy, you have what? Atomization, right?
Atomization.
Yes. For now, what kind of component that we have? Second one is detection. Okay. So the first one is what?
Separation.
Yes, separation, right? Okay. So now, for example, we have for the separation, we have high performance liquid chromatography. For the detection, normally we have UV. What is UV?
Ultraviolet.
UVVs.
Yes, UVVs, right? Ultraviolet and visible range of spectrum. Okay, so after being separate using HPLC, the detection can be made by UVs, or we have also what? Fluorescence. Okay, oh, maybe a wrong spelling, but the idea is fluorescent. Okay, so we have this is for HPLC. Now we have for GC. We have GC, the detection. What is? Can anybody give me example that you can, if you have heard previously or what? We have MS. What is MS?
Mass spectrometry.
Yes, mass spectrometry. Also, we have what kind of GC? FID. What is FID? We learn after this. Okay. So, light. The concept of the chromatography technique is light with light. Non-polar analyte, love, non-polar. SP. What is SP? Stationary phase. Okay. And polar analytes love polar SP. So what is non-polar and what is polar? For example, I draw a compound here. What should be at the end of the line? hydrogen, right? What is this compound? We have 3C. What is this? You learn during your matriculation or during your what? Propane? True? Class? Is it true? Propane? Hello, petroleum engineers wanna be?
Yes, yes.
Propane.
Doctor.
Okay. This is propane. Is it polar? Okay, what means bipolar in your own words? Polar bear, right? What is polar?
Straight line.
Huh?
Straight line. Single bond.
Not so accurate, not so accurate answer. What is polar?
Charge the valence.
Huh?
Charge the valence.
I can't hear you. Fansha. What's that?
Charge between the molecule is balanced. No positive and negative.
Which one? Here, propane. Okay.
Dia punya charge dia balance lah.
So now the propane is balanced or not?
Balance.
So it is polar?
Non-polar. Non-polar.
Yes,
Non-polar.
non-polar. Because the is balanced, right? So polar means that something that have different charge. Okay. Positive and negative. Okay. Polar, right? North pole, south pole. Okay. Which side of pole that polar bear live? Why the penguin are not being eaten by the polar bear? Because they are living in a different pole, right? Okay, now we have positive charge and negative charge. We have two type of charge, right? So when the compound has two different charge, okay, two different side of charge, okay, then this compound is polar. So for this propane, is it polar?
No.
Do you have any charge here?
No. Not
No,
polar.
right? So this is non-polar. Okay. Okay, let's see the simple that I want you to make the experiment and show me in the WhatsApp group for everyone, every single of you. Cut a bit of tissue and then you put one dot like this. Okay. Then put it in a glass. Put some water. Okay. Then you can see. Please, I want you make the simple experiment by your own self. Okay. And then show the photo for me. If you want to, selfie with your simple experiment also can, because I will compile all the photo, and then I will show in any of my social media. Okay, and we will select as the artist after this. Okay, right. This is the synthetic coloring agent from the marker pen. Okay, and this one is the organic. Okay, from the leaves that have color or the fruits. This is from the M&M. Okay, candy chromatography. Call it and make it by yourself. You want to choose candy, leaf, or any synthetic. But please don't only use this. Please be creative. Okay, and send me the photo with your own selfie. Okay, and send to me. Okay, so 5 simple steps in chromatography. Okay, now we have introducing the sample. Okay, we have to introduce the sample. We have to retain the analyte on the stationary phase. Okay, and then we have elution or stripping out the analyte. Okay, we have to remove the analyte, and then the separation occurred, and then we collect the chromatogram. So now, what is the chromatogram? From the spectroscopy method, we have the concentration as the result, right? We have to calibrate the instrument, and then remember calibration last week I taught you. Remember our previous class? Are you there or you sleep in the class? Remember the calibration? Okay. Remember the keyword I told you last week. What is you know, I told you the instruments, all the instruments are the keyword. Is a bad word actually, but that is a keyword I use normally. All the instruments are what? Class. Nobody speaking. Huh? Yes. You're afraid to say that. All the instruments are stupid. Okay. They don't know the concentration. Okay. So we who teach the instruments the concentration. So how we teach is using what? Using what? Azimuddin, thank you for your answer. You remember my class. Before I upload the video in the e-learning, but you remember what is the keyword, right? So how to teach the instruments? Ifan. Oh yeah, yes, we teach the instrument. How we teach the instrument? How do we teach the instrument? How? Yes, calibrate using a known concentration. Thank you, Rushdan. Okay, give a big clap to Rushdan. You can clap in the Webex, right? You know the clap button? Ah, there. Give a green clap to Rushdan. Yes, we have to calibrate. Okay, so in chromatography, the result will be in the chromatogram. Okay, it's like a graph. Okay, everybody clap to Rushdan. Okay, if you are in my class face to face, I will give you a present. Okay, somebody who answer my question, we have you know, a gift from me, no matter in the form of money or what. Okay, so pray that you can meet me face to face. Okay, I will pray that we cannot meet face to face. Okay. The result will be in the chromatogram, but still, for this chromatography technique, we need to calibrate. Okay, because the instrument are what? I want to hear from you. All of you said it. All
Stupid.
the instrument are stupid. Yes, because we create the instrument, so the instrument is not so clever, not so good, not so smart. Okay, so we need to teach the instrument. How to teach the instrument is from the calibration, right? Calibration plot. Why my slide is not moving? Okay. I am not finished telling you about polar and non-polar, right? So let us back again. So if the propane is non-polar, so what is the polar compound? Can anybody give me examples?
Water.
Water, good example. H2O, right? H2O. So what is the water looks like? The water molecules look like H double bond. Okay, O double bond H, and another bond is it true? Is it true? The water looks like the molecule of water. Anybody? You want to Google how the water molecules look like? Is it true? Like and draw here?
No.
Okay.
Single bond, single bond,
Single bond and
single bond.
single bond and single bond.
Ah.
Okay, good. Okay. Thank you for that because I'm just testing you. Water don't have double bond like that. So single bond, is it true like this? Similar with this one. Okay. Is it true the water look like this? Who gives me the example of water? Who gave me the example of what water as the polar compound just now? Is it true how the water molecules look like?
Yeah.
Okay. Is it true the H is opposite like this? O, yes, O normally have two negative charge. But what we have here is lone pair electron, right? The electron is not so good. Okay. Let me draw again. Okay. We have two lone pair electron. So how we said that the water molecules is polar? Why you said that the water molecule is polar?
Because the arrow polar does not cancel each other. The arrow polar goes to oxygen.
Yes, because a lot of electrons lone pair here we have at the oxygen. The water is the most polar thing, right? Because all the negative charge concentrated here and positive charge is here. And at the lone pair, normally water have another bond, hydrogen bonding with another molecule of what? Of water itself. Okay. Okay. H. Of course. So even the H in the HPLC, okay, the water will make bonding. Okay. Like that. All right. I'm just making a joke for that. You are not laughing with my joke. Okay. So that is polar and non-polar looks like, but you give okay. Okay, you laugh. Okay, that is I don't know either the laugh is ikhlas or not. Okay?
Lambat sikit.
Oh, lambat sikit biasa lah. Delay. Okay? Alright. So water is the most polar thing, right? But we have also another example of polar molecules. Okay? That I draw here. We have a lot of we have a lot of space here. What about this? What is this? What is this? Ethanol or methanol? Ethanol or methanol?
E.
Ethanol, right? Because we have two carbon. Okay. The compound is polar or not? So in hydrocarbon, also we have a polar compound. Okay. Because something that have oxygen or what, anything else that have a lone pair, okay, we'll bring all the electrons here. We'll favor for the electron to be here. Okay. So this side will be negative charge. Okay. And this side will be positive charge. So this is a polar compound. So remember in this example in HPLC and GC, the non-polar analyte loves non-polar stationary phase. And polar analyte love polar stationary phase. Meaning that if you want to detect the non-polar analytes, we have to use the non-polar stationary phase. And if you have to analyze the polar analytes, we have to use the polar stationary phase. What is stationary phase? A column. Okay. Right. Remember that. Okay. Just remember the non-polar love non-polar and polar love polar. Okay. And remember to do these simple activities at your hometown and send a photo to me, your selfie photo. Use your own samples. Okay. This is a step in the chromatography. We have to introduce sample. Of course, we have. If we want to analyze a sample, we need to put a sample. Okay. And then analyte will retain on the stationary phase. Let's say our sample we want to analyze a polar compound. So what kind of stationary phase we need to use? We want to analyze a polar. So polar.
Polar
Okay.
stationary phase.
Okay, good. Right. So elution, also known as stripping out the analyte. How to stripping out the analyte? What kind of phase that we want to use here? A mobile phase. All right. Okay. What kind of phase that we need to use for the stripping to stripping out the okay, so strip out the analyte. Yes. We have a cameraman. Yes. Yes. Okay. Okay. A mobile phase, right? Thank you, Mr. Cameraman. Okay. I will introduce my cameraman after this. Okay. Okay. Mobile phase. Terima kasih, Boh. Terima kasih, Boh. Okay. So, if we after we strip out the analyte, the separation occurred and we have our result in the form of chromatogram. Okay. So the first step, the solute or the analyte is introduced onto the stationary phase, which interacts with and retains, okay, the analytes differently. Okay. Look at here. Look at the photo. Look at the diagram. Okay. First, we put our sample inside. Okay. And then elution is process of washing components through the column by adding mobile phase, eluent or solvent. Okay. And then we put the mobile phase. So now, okay, the eluent carries the components for which it has affinity. Okay. Changing the eluent change the analyte's affinity for the stationary phase, resulting in separation of components. The mobile phase that exit the column is called the eluate. Okay. So when we put the mobile phase, the component, the compound starts to separated. Okay. Starts to be separated. Okay. Okay. Look at here, interaction with the stationary phase. Okay. So this one have the most interaction with the stationary phase. Because of what? Because when we put mobile phase, it doesn't want to get out from the stationary phase. Okay, dia sayang ketat-ketat kan, duduk kat sini je. Okay, and then this one is so-so lah. Kata sayang tak sayang lah. Okay, and this one yang paling benci lah. Okay, this one hate the stationary phase a lot. This one want to leave the stationary phase, okay, as possible as it can. Okay, so we have a different type of compounds inside here. Okay, this one want to interact with the stationary phase, okay, more than this one and this one. So we have separate all the compounds in the sample. Okay, so now we separated all the compounds, so we can identify, quantify, and what? we can purify, and so on, because we already separate. Okay. So chromatographic processes are classified according to the type of interactions or equilibration process involved. Okay. And then type of stationary phase. Okay. We have adsorption stationary phase. We have partition stationary phase. We have ion exchange stationary phase. We have affinity stationary phase. And we have gel permeation or size exclusion stationary phase based on size, right? So what is affinity? Can anybody give me the answer? What is affinity? Give your idea. Or you want to Google, up to you. What is affinity? Hello?
Attraction.
Attraction? Someone else? Bonding? Okay, you got the idea. Attraction, bonding, and what else?
Tendency.
Yes?
Tendency.
Tendency. Okay. So it's about the a bonding, a tendency, or what? Attraction of the analyte onto the stationary phase. So what is adsorption? What is adsorption? Azmira Hani, are you there? Can you give me the idea what is adsorption? Azmira Hani, are you there? Sarvin. Sarvin, can you give me idea what is adsorption?
Yes, sir.
What is adsorption? The first one. Adsorption. What is it?
Sir, do you want the example or just the meaning of absorption?
Just give me your idea about the meaning of adsorption.
The ability of an atom to exchange its energy.
It's quite a high level answer. Even I cannot understand. So just give me a layman word. You have heard about absorb, right? Absorb.
The ability to gain something.
Gain something. How about
Example.
attach
Example.
something? Attach something, right?
Yes, sir.
Okay. Thank you, Sarvin Kumar. All right. So you have heard about absorb word before this. Now, this is a not wrong spell. This is a right spell, which is adsorb. Adsorb, not adsorb, adsorb. Okay. Different of absorb and adsorb. So, okay, laptop hang. Hani, Hazmira Hani, can you explain? Or can you give your own idea what is absorption and what is adsorption? You can open your mic and you can try to answer what is the difference between absorb and adsorb. Or your laptop is still hang. So let me call another person.
Huh?
What? Yes, who's that?
Arvin.
Harvin, yes, Harvin.
for the word with the D, adsorption,
Yes.
is the situation where the molecule holds a particle of gas, liquid, or atom.
Hold. With B or D?
For the D.
D. And then what is for B?
For B, it will attach together. It's like gain.
Okay. So that is the keyword. Thank you, Savin Kumar. Between hold and attach. Absorb, okay, is forever attached. Okay. Let's say we have a compound here and we have an absorbent here. When it being absorbed, okay, with B, it will be forever here, absorbed. Okay. Cannot be released out. But if the word is adsorb, okay, the compound can be there in the adsorbent, okay, adsorbent, and can be dissolved, okay, can be released out. Okay, if this one absorb, it will never be released out. It will forever there. But adsorb, it will be released out again. So if we use absorption in the stationary phase, so it's not suitable because our analyte will never be released out from the column. It's still there. Okay.
Doctor,
Yes, who's speaking?
Sarwin again.
Sarvin again saying, okay, Sarvin, yes, what?
Doctor, for the word with the D, adsorption, is
Yes.
for the double bond molecule, is it?
Yes, what?
Is it for the double bond molecules?
It can be anything. Okay. If the word I'm differentiate between absorb and adsorb. Okay. If you see the word add with D, meaning that it can the compound, the adsorbent, it can adsorb something and can dissolve back, can release back. Okay. If the compound is absorbent, it absorbs something and it cannot be released back. It will attach there. Okay. So that is the difference between absorb and adsorb. Okay. So the concept in this stationary phase, one of the stationary phase type is adsorption, meaning that it can absorb and dissolve. Okay. We never use absorption concept in stationary phase because while when it absorb the analyte, it never dissolve the analyte. So it will retain there. So we don't want that. Okay. So we have adsorption, partition, ion exchange, affinity, sublimation. Because you remember, we need to remove out all the analyte after being analyzed, right? We use mobile phase, okay? Because the instrument or the column will be used again and again, okay? We need one of the criteria of the instrument. It can be repeatability. Okay, the process of analysis can be repeated. Okay, if we use absorption concept in the instrument, so the instrument only used for one time only. Okay, that is not economical. Okay, so we want to use again and again the instrument. So the concept meaning that the concept is repeatable. Okay, so that is the type of the stationary phase. So this is the family branch of chromatography. Okay, we have a gas chromatography, we have liquid chromatography, we have supercritical fluid chromatography. In gas chromatography, we have gas liquid and gas solid. In liquid chromatography, we have ion exchange and exclusion. Okay, and then we have partition chromatography, and we have liquid solid adsorption, and we have paper chromatography. Okay, for the partition chromatography, and then we have thin layer chromatography under the liquid solid adsorption. This one is the concept that you will use in your activity that I asked you to do. And supercritical fluid is on itself. Okay. So the most common instrument that we're gonna use in the industries is gas chromatography and liquid chromatography, right? Okay, now adsorption chromatography. Okay, the thin layer chromatography, HPLC, and GC also use this concept. Okay, the solution or the solute and the solvent compete for active sites on the solid adsorbent. Okay, remember I told you for adsorbent it can adsorb and desorb back. Okay, so it have active site for adsorption. Okay, so the solute and solvent compete for active sites on the solid adsorbent, and the active sites of the stationary phase, for example, silanols of silica, interact with the functional group of the compounds to be separated. Okay, this one is a compound to be separated. Okay, so it attached on the adsorbent surface. It been adsorbed here by, it can be hydrogen bonds, it can be van der Waals force, okay, and it can be hydrophobic interaction. Okay, so meaning that it's not a kekal selama-lamanya. Okay, it's not a forever attachment there. It can be released out again. Okay, as relative adsorption of the mobile phase is increased by manipulating the eluent. Remember what is eluent? The mobile phase. Okay, adsorption of the solute is decreased, thus eluted. Okay, this step is you want to release back the solute or the the analyte on the stationary phase. This one is stationary phase. Okay, and it uses adsorption concept. So it has an active site for adsorption, and then the analyte attached here being adsorbed here. All right, and then when we put our eluent or mobile phase, it being released out again, so we can adsorb and desorb. Okay, when it being adsorbed, so there we analyze what is the analyte. Okay, so partition chromatography or paper chromatography, how it works. Okay, based on a thin film force on the surface of a solid support by a liquid stationary phase. Okay, it is based on thin film formed on the surface of a solid support by a liquid stationary phase. Remember, we have also liquid stationary phase. Okay, solids are partitioned between two immiscible liquids. And then the system is manipulated by changing the nature of the two liquids. Okay, what is the two liquids? Okay, the two immiscible liquids. Okay, what is the word immiscible? Somebody can tell me? Can search it for me? The meaning of immiscible. Okay, Hasmira Hani, thank you. Addition. Okay, addition, attraction between
Homogeneous mixture.
homogeneous mixture. Okay, Anis, who said that? Thank you. Okay, immiscible means homogeneous. So the two liquid being homogeneous, then we can manipulate all the two liquids by changing the nature. Okay, and so this is inert solid support, the stationary phase. This is a stationary phase. So on the surface of this inert solid support, we have the two liquids. Okay, the two homogeneous liquid that we can play with the what? All right, we can play with, we can manipulate with the nature of the two liquid. Okay, for the analyte to attach on the surface. Okay, and then we can release it back. Okay, using eluent. So this is how a partition chromatography, and we have also ion exchange chromatography. Okay, this is our stationary phase. Okay, separation is based on the difference in the affinity of charge stationary phase for charged species. Okay, so for the ion exchange, for example, we have negative charge here on the surface of the stationary phase. So the positive charge analyte will attach on the positive charge stationary phase. So, and the stationary phase ion exchanger contains fixed charge functional group and exchangeable counter ions. Okay, and ions or charge sites on large molecules exchange with the counter ions same charge with ion of the stationary phase. Okay. Faham tak? You understand? The stationary phase, okay, the ion exchanger here contains a fixed charge. This charge is fixed. Okay. And exchangeable counter ion. So it also have an exchangeable counter ions. Okay. And the ions or charge sites on large molecule, okay, exchange with the counter ion with the same charge with ion of the stationary phase. Okay. So the analyte that have the opposite charge of the surface of the ion exchange chromatography stationary phase, it will attach. Okay. And then it will be exchanged with the counter ion, okay, with the same charge of the ion of the stationary phase. Okay. Right. So negatively charged analyte, anion, attract to the positive surface. For the positively charged analyte or cation, it will be attracted to negative surface. So this is the basic of ion exchange chromatography. So components attached to the ion exchanger, okay, are eluted by changing the mobile phase property again. Okay, again, if you want to elute out, okay, all the analytes, okay, for the next analysis, because we don't want our analytes or our sample retained there in our stationary phase, we need to elute it. Okay, we need to remove all the analytes by changing the mobile phase property. Right. So this is the example of the resin type and the cation exchanger and anion exchanger. Okay, the net charge of a molecule of interest is positive. Okay. Okay, and then the charge resin, if the charge of the molecule, if the cation exchanger is positive, so charge of resin is negative. It will be opposite. Simple. Okay. Size exclusion chromatography, SEC. Separate molecules based on the size difference. Okay. We have, for example, this is a stationary phase. Okay. Like a Pac-Man, right? We have played a Pac-Man game. Okay. We have, so we have now 1, 2, 3 different size of the analyte. Okay. So it will separate the molecules based on the size difference. Okay. The stationary phase contains porous material. What is porous? Pore is like the small hole. Okay, this is pore. The hole itself is pore. So can this big one attach here? No, of course. It select the size. Remember that I told you I put you in one closed room and I make a small door there so that only those who have a weight or the size or a weight under 60 and below can pass through the door. So this is the example. So this is the size exclusion chromatography. So the pore is specific for a certain size. Okay. And stationary phase contain porous material that have pore comparable to the size of components. Smaller size molecules are retained longer in the pores, thus eluted later. Okay, large size molecules are unretained by the pores, thus eluted early. So SEC, size exclusion chromatography, requires calibration using a series of known standard solutes. Okay. So again, we need to calibrate the instrument, okay? Because we have a stationary phase that have the pore size that is with known pore size, okay? And then how it's how it separate the analytes in the compounds is by the size difference, okay? The small size will retain longer in the pore, while the big size will easily unretained, okay? Easily move out from the column, from the stationary phase by when we eluted, we put mobile phase. So the small size will retain longer in the pore rather than the large size. Simple concept. but we need to calibrate with the known calibration standard. So the calibration standard should have different size. We know our calibration 1 have size 1. Our calibration 2 have size 2. Our calibration 3 have size 3. Okay, so we calibrate the instrument, and then the instrument know exactly the size representing what type of compound. Okay, and now we have affinity chromatography. Okay, separation is based on the specific and reversible interaction between a solid molecule and a ligand. Okay, right? A molecule is proteins or enzyme, and a ligand that specifically interact with the molecules to be isolated is immobilized on the support material. Molecules that are complementary to the ligand are adsorbed. Other components are eluted. So this is very selective. Sangat memilih kan. Like an enzyme and protein, lock and key. Okay, it have a certain shape or size that only can attach with the stationary phase. Okay, molecules. Adsorbed molecules are eluted via exchange in the mobile phase composition. Again, the adsorbed molecules are eluted, can be eluted back. Okay, can be removed via exchange in the mobile phase composition. Okay, we can remove back the analytes or the sample from the stationary phase. Okay, remember the lock and key concept in the proteins and enzymes. You learned that. Okay, so only certain proteins can attach on the enzyme. Okay, for example, it's a support matrix and this is the analyte. Okay, can the impurities attach here? No, right? Only the analyte that we want that have a certain shape. Okay, like this is a key and this is a this is a lock. Okay, can attach. Okay, the impurities. Okay, bye bye. Okay, it cannot be attached on the stationary phase. Okay, and then we put back our mobile phase to remove back the analyte to be eluted out from the stationary phase. So now also we can analyze based on the affinity, based on the interest. Okay, the concept is like proteins and enzyme, lock and key. Only the certain shape of the analytes, okay, can attach on the stationary phase. Okay, so the stationary phase is well designed for certain analytes. All right, so this is chromatogram, the graph that being produced by our process in the previously we used stationary phase, mobile phase, okay, with different technique, affinity, ion exchange, size exclusion, and so on. So it will produce a graph like this. So this graph we call as chromatogram. The tracing of the output signal versus time or eluent volume. Okay, this is time. Remember, we separate based on various kind of technique, but at the end we know the time of what it can be eluted. Okay, when we put mobile phase, which one will eluted out first? The first compound that being eluted out will appear first. Okay, the compound that retain longer in the stationary phase will come after that. This one is the most longer. Okay, this compound loves the stationary phase so much. Okay, cannot say goodbye to the stationary phase, so it will be the last compound that appear on the chromatogram because it's hard for the mobile phase to push it out. Okay, so the first compound that leaves the stationary phase will come first. Okay, and this is the signal. This is time. Okay, analytes differ in their affinity for the stationary phase versus the mobile phase. Each analyte exhibits different retention or migration and elution patterns, and thus a mixture of analyte can be separated and quantified. Sorry. So that is the concept of chromatography. Okay, we design a stationary phase and mobile phase that can attach the analyte and detach the analyte. Okay, So based on interest, which one will go out from the stationary phase will appear first in the chromatogram and followed by another compound. Okay, so this is the concept of separation technique. Separate. Okay, we separate based on that. Okay, based on the ion exchange, based on the size exclusion, and so on. And after that, we know the compound will be separated. But even though sometimes maybe two or more compounds are being separated at the same time, meaning that the chromatogram is overlap. So we use another technique to separate the chromatogram of the different analyte that appear on the same chromatogram, right? So characteristic of the chromatogram, right? This is the injection. This is the first time that we introduce the sample into the instrument. We inject the sample. And then when we wait for a certain time, then appear one peak here. After that, again, we have one peak here, right? And we wait for a while. After that, we have another peak here. Okay. Okay. The first injection, the time between first injection and the first peak is T, for example, T naught, okay, T0. And then for a second peak, okay, we have TR1. And then for the third peak, we have TR2, okay. Okay, so this is the peak. Okay, T naught or Tm is the void volume or dead volume, is the retention time of unretained compound. Okay, what is meaning by the retention time for the unretained compound? Right? Can anybody give me the meaning of the unretained compound? Why only both of these thing is our peak, peak from the analyte, but the first one is T naught, is the void volume or the dead volume, is the retention time of unretained compound. Okay, Hakim Pauk said that time taken for solute to pass through column. Okay, so what I mean by that? Anybody? Hakim Pauk, can you explain that more? Time taken for solute to pass through column. What is solute? What is a solute?
Hello, Doctor.
Yes, can hear you. Okay, explain that.
The taking for solid to pass through the column. So the solid,
Louder.
solid,
Okay.
we as the like time taken for solid to pass through the column ni like macam is calculate the time from injection to the detection. Is it answer your question, Doctor?
Again.
The time that calculates
Okay.
from the injection to the detection. Is it answer your question?
It's quite you can explain it more. Somebody can explain it more. so that your friend can understand? Thank you, Hakim, for your answer.
Thank you, sir.
Hakim said that the time taken for the solute, okay, to pass through the column. Yes, it did. But can you explain more? What about the second peak and third peak? Why does this peak is not counted? Okay. Okay, in the solution, we have the unretained compound that does not interact with the stationary phase at all, right? It will be eluted out at the first, with a small peak, okay, at the first time of at the beginning of the analysis, okay? And then the peak from the compounds that we need to analyze will come out, okay? Thank you, Hakim. Okay, TR1 and TR2 is the retention time between retention time for separated components 1 and 2. You need compound 1 and compound 2. Right? And then the W1 and W2 is width at base peak of components. Okay? The width, okay? The size. Okay, the width is the what we call in Malay is the apa width? Ketebalan. Okay? At the base peak of the component. Okay, chromatographic definition and calculation. So retention time, TR, is time elapsed between injection of sample and emergence of peak maximum. And then the mobile phase, hold up time, T0 or TM, is time required for an injected solvent or any other unretained compound to traverse to the column, also known as dead volume or void volume, meaning that we put our mobile phase right inside the to inject or to elute the sample inside the stationary phase, and then the first peak appear might be from the solvent itself, okay, or any compound that unretained in the stationary phase. Okay, in that the compound is doesn't react at all with the stationary phase. That is not our interest. So adjusted retention time, okay, T apostrophe R, is the difference between analyte retention time and column void volume. This one is adjusted. Okay, we minus the dead volume, okay, or the void volume, and then we get the adjusted retention time. Yes, thank you. All right, so retention factor, also known as capacity factor, K, is a measure of how long a sample is retained with respect to the dead volume. So TR minus T naught and divide by T naught. And the solution RS, okay, how well two species separate from each other. Okay, the degree of separation of two components leaving the column. So RS is equal to 2 R1 minus TR1 minus TR2 divided by W1 plus W2. So what is TR1? Okay, this is TR1. Okay, minus TR2. Okay, there is TR2. Okay, TR1, TR2. Okay, 2 TR1 minus TR2, and then divide by W1 plus W2. Okay, W1 plus W2. Okay, then we have the resolution. Okay, degree of separation of two components leaving the column. Okay, this is a sample problem. Given the following data and figure, calculate RS. Okay, now you have your example. So let's calculate. So calculate RS now. What is the formula for RS? Oh, fast answer from Ifan. Okay. RS is equal to what? To what minus what?
TR1 minus TR2.
T
R1 minus
R1 minus T R2 divide by W
W1 plus W2.
plus W2. So the answer is answer is 2.1 from Irfan. Everybody agree with that answer?
Yes.
Okay. So that is how to calculate RS. All right. RS larger than 1.5 means that they are well separated. Okay, remember, RS is more than 1.5 meaning that they are well separated. Okay. RS that lower than 1, okay, meaning that unresolved or bad separation. Meaning that we have, for example, for this solution 0.5, the two peaks appear in one. Okay, it's really bad. We can differentiate the both two compound, but and also one of the type of the unresolved or bad separation is when the peak is seems to be separated, but it's not completely separated. There are overlap. Okay, so this is also bad separation. Okay, if RS is equal to 1, this is 98% separated. Okay, but still overlap. Okay, and RS is 1.5 is the value of the starting value of completely separated two compounds, well separated. But this is the minimum required value for RS 1.5. This is meaning that it start to being well separated. Okay. So what is the separation factor? Okay, or selectivity factor, alpha. A measure on how good a column can separate two substances by their different chemical properties for a given mobile phase. Okay, for two species A and B, the selectivity factor alpha, okay, is equal to TRP minus T naught divided by TRA minus T naught, or equal to T apostrophe R B minus T apostrophe RA, or equal to K apostrophe B minus K apostrophe A. What is K? Previously, we know, where is K? Oh, here. Okay. The T apostrophe is adjusted at a certain time when we minus with T naught, right? And then K is the retention factor. TR minus T naught divided by T naught. Okay, so the equation is as simple as we will replace, okay, only with KB minus KA, meaning that the difference of K apostrophe equal to the alpha, the selectivity factor. Okay. This is for example. We have a chromatogram here. This is the injection time, all right? This is the T naught, okay, for the air peak, and then we have A and B, okay? So the alpha is okay, T apostrophe R, okay, divide by T is for R for B. Okay. Why put divide by here? Okay. It should be a minus. Okay. All right. So we have K apostrophe B and K apostrophe A. Okay. All right. And then we have the alpha value is 1.4. So there is the selectivity factor, a measure on how a good column can separate two substances by their different chemical properties for a given mobile phase. Then improving alpha gives the strongest contribution to improving RS. Okay. Understood? My slide is not moving. Okay. So column efficiency or theoretical number of plates, N, a measure of the broadening of the sample peak as it passed through the column. A good efficiency corresponds to small peak or bandwidth with the symbol of W. It depends on the flow rate, column length, and diameter of particles in the column packing material. So what is the equation? N equal to 16 TR divided by WB, okay, the power of 2, or N equal to 5.54 for TR naught divided by W half, okay, to the power of 2, where WB is a bandwidth of peak, also known as base peak width, and W half is the width of peak at half height. So this is the equation. Either we use W or W half. Okay. The higher the N value, the more efficient the separation is. So remember all the factors. Okay. Remember all the formula. Okay. RS. Okay. For the sample for the resolution. Okay. RS. And then remember the alpha. Okay. And remember also the N. Okay. All right. For the chromatography method, fractioning column, we have N value 5 to 1,000. For HPLC, we have 50,000 to 200,000. For the GC, we have 1,000 to 1 million. Okay. For capillary electrophoresis, we have 100,000 to 1 million. Okay. The higher equivalent to a theoretical plate or plate high HTP or H is compares column efficiency N or of different length. The more efficient the column, the more theoretical plates N is. N in the column. And the better the resolution and the smaller the HATP or H. Okay, the sample problem. An analyte with a retention time of 407 a second has a width at the base of 13 seconds on a column 12.2 meter long. Find the number of plates N and plate height H. Right, now calculate. Okay. So we get N value is 1.57 times 10 to the power of 4, and H value is 0.78 millimeter. Okay. So where does the 16 come from? Because it is from formula, right? 16 T R square and WB square. So just put the figures. Right? What is T? T TR. What is TR? .407, right?
Oh,
Okay, and then what is the value of WB? The peak width, the base peak width, 13. Okay, and then just put a figure, and then we get the answer, right? The separation of mixtures depend on the width of solute peaks. Okay, we want narrow peaks for efficiency, and spacing between peaks, we want large spacing for resolution and selectivity. Remember these two things. We want the narrow peak, okay, for the efficiency, okay, and then we want the spacing between peaks for the resolution or selectivity. Parameters that affect the solution is the column efficiency. More N give narrower peak and better RS. The capacity factor K, if low K, analytes will not be retained enough for good separation. And then selectivity, if analytes are very similar, K1 almost equal to K2, then difficult to separate. Wait for a while. All right, sorry. So effect of N and alpha on RS. So for example, N is 250 and RS is 0.8. Okay. So it's poor RS and bad calibration curve, right? And 250 and RS 1.8 is a same N increase RS. It is better right now. And then if N is 1100 and RS 1.8, increase N, okay, we the same RS value with better calibration curve, right? So we have a quite sharp peaks, well separated, right? And effect of N and alpha on resolution. The first one is a poor resolution, okay, and the second one is a good resolution due to column efficiency. And the third one is a good resolution due to column selectivity. Remember, efficiency and selectivity is more efficiency, meaning that the peak is quite sharp, okay, and good resolution meaning that the column the column selectivity is good, the solution is good, well, meaning that the two peaks will be well separated. And the last one is poor solution despite adequate column efficiency and selectivity, a low K. Right? This is quite sharp, but it's not so not well separated. All right, thank you. That is for our first topic. Successfully for this class session, we have finished the introduction of the chromatography methods. All right, and now I will open for question. If you have questions, how about our class today? You understand the concept of chromatography? Okay, you know the concept well that I explained today. So please give your response, or Ifan, give me thumbs up. Okay, so what about you, all of you? You have questions? Our international students from Saudi, Aziz Belmahdi, Abdus Samad Dayib, okay? Kehat, you have any questions? Do you understand what I'm talking now?
Yes, doctor. Actually, I'm in Johor, sir.
Sorry. You're in Johor now. So, who's in Saudi? Kehat or who? I forgot. Because we have our Egyptian friends here, and also yes, Aziz is at Saudi. So how's Saudi right now? Can we perform Umrah right now or not yet? Very cold. Oh, what is the temperature there right now? We are also cold here at Johor Bahru, but not so low temperature. It's only raining. Umrah is closed. Okay. No, that's sad. So it's very sad to see that nobody there at the Kaabah, no? During the first wave of the pandemic, where we see the Kaabah without nobody perform tawaf around it. So it's very sad, right? Because I have been there for Umrah previously, about last 10 years, right? Nuri Irfan, Malaysia is -1 degree Celsius. In your freezer or what? All right, Aziz, yes, true. It's really sad to see the Kaabah. Oh, Nuri Irfan cannot mandi. You don't mandi yet. It's really good, right, to have an online class on your bed, right? Without brush your teeth, okay? And your mom keep yelling to you, where you gonna wake up from your bed? I have a class, mom, right now, right? You said that to your mom. Saudi is 10 degree. Wow, that's really cold. Okay, you have questions? Okay, so thank you so much for today. I will upload our recorded class for today and our previous class last week in the e-learning. All right, thank you so much. All right, for being to stay with my class. Okay, for 2 hours. Okay, for our important topic for today is introduction to the chromatography, and after this we will learn specifically on the instrument HPLC, GC, and so on. Okay, we are now approaching, at the very end of the semester. We will learn all these final topics. All right, and thank you so much. Okay, Assalamualaikum and bye bye.
Thank you, Doctor.
Most welcome.
Thank you, Doctor.
Welcome.
Thank you, doktor.
This is the most
Saya
important
nak
part
mandi,
of the class.
doktor.
Everybody say thank you to me. Yes? Who's speaking?
Saya nak mandi, doktor.
Tak mandi? Okay, Alhamdulillah.
Alhamdulillah.
Macam-macam
Thank you. Okay, welcome. Anybody want to scan the attendance?